Hello. Could you please confirm if I'm audible? Hello. Am I audible, everyone? You can type in the chat box. I cannot hear you. Okay, fine. Yeah. So let's start today's session. So welcome to the live session for week 6 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad, and I'm Anant Singhal, PhD student from IIT Jodhpur, and I'll be assisting in solving similar problems which are related to week 6 assignment. That will help you in solving the assignment that has been given to you for the week 6. So till now we have already covered uh, the content till week 5, which was basically related to more towards the physics of the devices, such as the motion of carriers, the carrier properties, etc. And then we went towards our first device that was the p-n junction diode. We read about the p-n junction electrostatics, how the band diagrams are made, etc. And then in the last week we basically covered how does a band diagram or the characteristic changes if we apply certain bias to a p-n junction. So in this week, we'll be more of reading about some of the diode non-idealities, like what happens when we apply a certain voltage. What are basically the major topic for this week will be the metal semiconductor junctions, uh, in which what happens if we have a very high doping, etc. And uh, these junction will be covered in this particular week, and we'll like have a very basic overview of the diffusion capacitance that occurs when we apply a certain positive bias across a p-n junction. uh, so let's start to today's session. Maybe I'll give you a very basic overview for the last class, and then we'll start. So in the last class we have read about p-n junction under forward bias. So if I talk about equilibrium, so let's say we have a p-n junction under equilibrium. So what we studied is, let's say we have a conduction profile like this. So what we studied is we have a certain built-in potential that is helping in maintaining this equilibrium, which is denoted by QVBI. If you remember from the last classes, we have certain electrons at the n side, which are getting the equilibrium is getting maintained between this p and n side using this built-in potential, which we gave out by the relation VT ln NAND by Ni square. So this is what I'm talking about, the equilibrium condition. So what I can write in very basic is this NAND by Ni square is nothing but exponential of VBI over VT. So if I talk about, let us assume that we have complete ionization, because that is what we generally assume for all the derivation and the cases. So let's say we have full ionization or complete ionization. So we know that complete ionization means that the equilibrium carriers, that is N naught at the N side, is nothing but ND. So what I'm trying to denote here is N naught is nothing but the majority carriers, because at the N side the N naught will be the majority carriers. So majority carriers or the electrons concentration at thermal equilibrium. So this naught is denoted for the equilibrium part at N side. So if I just write NN, that will mean again the majority carriers. So I'm not writing it again. The majority carriers at N side again when it is not in equilibrium. So basically this not is denoting the equilibrium part, and this Nn is nothing but out of equilibrium. So this we already know that at the majority side Nn naught will be Nd, or if I write even Pp naught, that will be Na for a PN junction. So let me give you some quick terms so that it will be easier to grab it. So let's say I have Np naught. So P naught means that we will have minority carriers now. Minority carriers that are electrons, because we are writing N at P side now, at equilibrium, because we have a knot. Similarly, if I write Np, so that will again be minority carriers that are electrons at P side, which are not in equilibrium. I hope you are getting the analogy what I am trying to write. Similarly with Pp naught will be majority carriers that are holes, again at P side, because we are writing P, and it will be at equilibrium because we are writing a knot. And similarly we can write for Pp that will be not in equilibrium, then we can write for Pn naught, which is will be opposite to this Np naught. So Pn naught will be minority carriers. So since we are writing N, so now this will be minority carriers will be holes. So N naught means at N side at equilibrium. And same which we have left with Pn, so this will be same, which is not at equilibrium. So these are all the analogies. So as we know that, as I have written in the previous slide, that Nn naught is nothing but Nd. The majority carrier at N side is Nd, and we know that N times P is Ni square, from which we require, or which from which we will calculate the minority carriers in general. So this is how we get the relation, if you remember from the last classes. So now these are the minority carriers. So this will be nothing but the holes at sorry, the electrons at P side will be the minority carrier. So it will be nothing but Ni square over Na. So it will be at equilibrium again. So what I can write is, I can write maybe I have given you this relation. So I'm writing it again. So I had a relation Na by Nd over Ni square is exponential of Vbi over Vt. So here I can write that, sorry, Ni square by Na is nothing but Nd times exponential of Vbi over Vt. This is purely mathematics. So I have just done the opposite. So Ni square by Na will be Nd times exponential. Yeah. So I guess this is, so this is what I'll be putting this in this equation. So this will give me Np naught, that is Np naught will be nothing but, so what I have is Nd. So Nd is nothing but Nn naught, that we already know, and exponential of Pbi over Vt. Or what I can write is Np naught. Okay, I guess I've written this inversely. This will be minus. So what I can write is Np naught is Nn naught exponential of minus Vbi over Vt. What it implies is we have the majority carriers which is getting multiplied by a lesser term that is giving me some minority carriers. So this is what we have relation when we are in equilibrium. But when we apply the bias voltage, as we discussed, when we apply, let's say, a certain positive bias, let's say this is Va. So what we have is we don't have a thermal equilibrium anymore, and the majority carriers starts crossing the space charge region, because as we talk about the PN junction, so if we apply a positive bias, so let's say a positive bias is here, a negative bias is here. So positive means these electrons which are on the n sides will move towards, the diffusion will happen towards the positive side, and the holes that are on the p side will diffuse towards the negative potential. So more diffusion happens once we apply this Va bias, and the major change that we have is in the diffusion of the majority carriers. So that will be nothing but, so at non-equilibrium, I'm writing the same relation now. But now what I'm doing is, instead of applying the barrier, we have an additional VA voltage, that is a positive bias, that we already know. So I can write this as NP, which is, now it is already, if I just broke it in two terms, so this will be exponential of minus VBI over VT and multiplied by exponential of VA over VT. So this is what we just read. It was nothing but NP naught and times exponential of VA over VT. So this is how we get the profile. So this is for the n side. So if I draw a PN junction, maybe you have read this plot. So this is, let's say, 0, this is xn, this is xp minus xp. So for n side, what we get is np is nothing but np naught exponential of VA over VT. So let's say this is the, sorry. So this is p side and we have electrons. So this is how it will look. And similarly, if we apply the positive bias here and do it for p positive side, so we will again achieve the same relation, which will look something like Pn will be Pn naught exponential of V over Vt. So this is how we get these profile, and this is what we have already discussed in the previous lectures also, that this is how a p-n junction works. If we have a more positive potential, we will have more diffusion, that is we have a smaller depletion width. And once we go for the reverse bias, so we talked more about the reverse bias because it is more important in the previous lecture. So once we have a reverse bias, we have a widened depletion width. So if I remember, if I make you remember from a very quick question, so let's say we have a temperature which is given as 300 Kelvin, and we have Ni which is 1.5 times 10 raised to the 10 per centimeter cube. So let's say we have a silicon PN junction again. So N-type doping Nd is given by 10 raised to the 16 per centimeter cube, and it is forward biased using the voltage, let's say 0.8 volts. Again, the doping is same, not doping, but the temperature is same. So what we need to do is we need to calculate the minority carriers whole concentration. So whole minority carriers will be there at the n side. I guess this is very understandable. So at the edge of the space charge region. This is what we need to calculate. So do you want to give it a try, or shall I explain directly? I have just given you the formula and the understanding for the same. This is very easy. If you want to try, you can write in the chat box that you are trying. Otherwise, I'll solve the same. So minority carrier whole. So that will be P at n side. So this is what we need to calculate at edge. I have already given you the formula. So at equilibrium, we know that we have Pn naught, and at the edge. So let me, maybe I can solve this directly and then you can try the more. So we need to calculate Pn, which is nothing but Pn naught times exponential of Va over Vt. And then Pn naught we know because it is minority carriers, so it will be Ni square over majority carriers, that are Nd for the n side. So maybe I can write all the values. Nd I have given it as 10 raised to the 16, so this will be 2.25 times 10 raised to the 4 per meter per centimeter cube. And the minority carriers now at the edge will be 2.25 times 10 raised to the 4 exponential of Va over Vt. So the forward applied bias is 0.8 and Vt is 0.026. So once you solve it, you will get that at the edge we will have a very high concentration of the the minority carriers, that is coming out to be 5.18 10 raised per 17 per centimeter cube. So basically what we have calculated is at the edge, what is, so holes at the end side. Sorry, holes at the end side will be, yeah. So we have a very high concentration at the edge and then it decays exponentially. So this is 0, let's say this is x and this is minus xp. So this was a very brief overview for the forward bias PN junction. Now I'll be maybe we are talking will be talking more about the main topic for this lecture, that will be nothing but the metal semiconductor contacts that we'll be talking about. So now we'll be talking about metal semiconductor junctions. So let's move ahead. So I'll be taking all the different cases that we can have. So the first case that I'll be talking about is a metal N-type semiconductor junction. So we have a N-type semiconductor and we have a metal and we are having a junction for them. And one more thing that I'll highlight here is the work function of the metal is greater than the work function of the semiconductor. I'll let you know why I've written this and what it is. So let us assume that the work function of the metal is greater than work function of semiconductor. So what happens is, we know that when we make contact, the work function of the metal, let's say I'm denoting it as phi m, and the electron affinity of the semiconductor, let's say this is chi s, it will not change because this is nothing but material property. So what happens is, so what I'm trying to write here, let me maybe make a band diagram. So the case is phi m is greater than phi s. So let's say this is some vacuum level. So what I'm trying to say is, let's say this is for metal, this is EF, this will be phi m. So the energy required to move an electron from Fermi level to the vacuum level is nothing but the work function. And the second thing that I'm trying to write is, maybe I can take N type of metal that I have asked for. So let's say this is EC, this is EF, the line that I've just drawn. This is, let's say, EI, and this is EV. The vacuum remains the same. So yeah, be attentive here. So the semiconductor work function will be the energy required from to move an electron from the Fermi level to the vacuum. So this will be E vacuum, which will remain same. So you can clearly see that in this case phi m is greater than phi s, and this is nothing but the energy required for removing an electron from conduction band to vacuum is nothing but the electron affinity. So is it understandable till now? Any doubts in this? How I have written phi m greater than phi s?
Clear, sir.
Okay, so we know that once we have the contact, what happens? The electron always flow from higher Fermi level to a lower Fermi level that we have already discussed in previous classes. So electron flow will be like this, and what will happen? This will get bent. So let me make the contact diagram now. Maybe I can take the vacuum like this. Let's say this is phi m, and I'm aligning the Fermi level. Let's say this is the Fermi level. So what will happen? To align, we will have some bending like this. I hope you are all able to understand that since we have a higher Fermi level, so this will go below and the band will bend upwards. So this will go here, and the band that we have, like this will come here and the band will bend upwards like this. So this is what I'm making when I'm making the diagram. And yeah, I guess this is enough to have a view. So what we will have, we have a n-type semiconductor. So what we have is, we have electrons here that will feel some barrier that we already know. Oh, sorry. That we already know is nothing but VBI. electron will feel some barrier, and what we have is so this is what we call the barrier as the barrier height, which is denoted by q phi b. This is ec, this is ef, this is ev. So now what is happening, we have a barrier and we have accumulation of nd plus here. So this is what we call as the Schottky contact, because we are feeling a barrier, the electrons are feeling a barrier. So what I can say is, here at the junction there is a massive barrier, so I'll write maybe implies massive barrier, and the barrier height which is denoted by phi b in the diagram. So here the electrons of the metal, which is this side, so this is metal, this is n-type semiconductor. So the electrons of the metal, they will experience a barrier, massive barrier, that is this barrier, right? So the electrons that are here will not be able to go this side. So that is why the conduction will not be easy. And similarly, the electrons in the semiconductor are also experiencing a barrier, which is again the same as VBI, and it will not be the at much steep, but this kind of contact is not going to give the ohmic result. So let's say I'll take the second case in which you will see that there is no barrier and it will easily conduct when we have the phi m or the phi s is greater than phi m. So when I'll take this case, you will be able to understand that. So this particular case will not be able to conduct easily because we have barrier on both the sides. So that is why we call this barrier as a Schottky barrier. So when phi m is greater than phi s and we have a metal n-type semiconductor, then we have a Schottky contact. So now what maybe you all can try is, you can take the case that will make it more clear. You can take again a metal n-type semiconductor, but this time take phi m less than phi s and try to make a band diagram out of it. The contact band diagram. So once you will make it, you will be seeing that the electrons will not be experiencing any barrier, and it will be having a ohmic contact. So do you want to give it a try, or shall I make the hello? Uh, am I audible now? Please confirm, guys, if I'm audible.
Yes, sir.
Okay, fine. Yeah, so let's continue. So what I was saying is to make the band diagram for a metal n-type semiconductor when this phi m is less than phi s. Yeah, so let's try it out now. So since I've given phi m is less than phi s, so let's say this is the vacuum level. So what will happen? Let's say I'm taking this as phi EF of metal side. So this will be phi m or q phi m. So now what we need to take is, we need to take the Fermi level below. So this is still n type. This is EI. This is EV, and let's say this is EC. So now what I can write here is, we have phi s here, and this is nothing but chi s. So here we can clearly see what we have is phi m is less than phi s. So now we have the electron flow like this because we have a higher Fermi level, and we know that metal have plenty of electrons, so there will be no problem in that. So this will go down. That means the bands will bend like this. I hope you understand this point. So let me try to make the contact diagram now. So let's say I have a Fermi level aligned. So what has happened now? Maybe Yes, so this will be EV and this will be EI. So we have a single Fermi. Now we can clearly see that this is N type and this is metal. So metal, so the all the electrons that N type semiconductor is having will be easily flowing through this. There is no barrier. And we know that metal is already rich of electrons. So that is why we call this contact as ohmic contact. So we have basically two types of contact. One is a Schottky contact in which there is a barrier, and the second one is a ohmic contact. So what we have is, so this is what we have done for the metal and the N type of junctions. So we can have again two more cases. One is metal P type semiconductor junction. For one of the case we have phi m greater than phi s, and similarly we can have P type semiconductor junction phi m less than phi s. So can anyone tell which one will be Schottky and which one will be ohmic? Maybe you can try to make the band diagram for the first case and you will get to know that which one will be ohmic and which one will be Schottky. Do you want to draw the band diagram or you want to tell directly, maybe if possible?
Phi m greater than phi s will be ohmic.
Okay. And why is it the case? So you have said phi m greater than phi s will be ohmic. Okay, give me a moment again. Okay, okay, just leave it. Yeah. So if I make a very quick diagram, because we have now P type semiconductor with metal. So let's say I'm making EF here, and maybe let's say this is EV, this is EI. So we have P type, so we'll have the EF here and EC here, and let's say this is the vacuum level. So phi m is this and phi s is this. So I mean we can make it a bit lower. So here we can clearly see that phi m is greater than q phi s. So what we'll have an electron flow like this, right? So now a key thing to notice here is because this will go down, so the bands will go up like that. So once the band will go up, so in P type what we have is we have the majority holes. So holes, what they prefer is they prefer to go up the hill very quickly. So there will be no barrier that will result in the ohmic contact. Similarly, if you will make for phi m less than phi s, so we will have a hole that are getting accumulated and there will be barrier and that will result in the Schottky. So I'm making it very quick because this is very straightforward. You can make the band diagrams for both Schottky and ohmic for these two cases also. So basically to summarize the context that we have, yeah, I can do here only. So we have two types of metal semiconductor contacts. So one is metal with N type semiconductor contact. One is metal with P type semiconductor contact. In this also we have two cases. One is phi m is greater than phi s and one is phi m is less than phi s. In this also we have two cases. So this phi m greater than phi s is resulting into Schottky for metal N type, and this is ohmic. Wherever this is ohmic and this is Schottky. So this is a very basic conclusion that we have drawn till now for the metal semiconductor contacts, and we'll be dealing with the questions for these topics only in this particular lecture. So yeah, so let's move ahead to some of the questions that we have for Schottky diode. So now, as I was saying that this is semiconductor contact. So if I'm saying that it is a Schottky diode, what it is mean that we have a metal and we have a long enough N-type semiconductor. So that we'll be calling as Schottky diode. So that is fine, I guess.
Sir, why specifically long enough?
Because contact is just, yeah. So that is a good question. So let's say we have a metal and we have a, let's say, some semiconductor. So if I'm talking specifically by naming it contact, so we are more interested towards this contact part only. And once we have a long enough metal and similarly it goes with the PN also. So we have a PN junction with a long enough bar. So what we call it as PN junction diode. So similarly for Schottky, we need to have some long enough bar. So that is why I said long enough. So this will be Schottky diode. uh, Before this we were analyzing the contact, how it will be Schottky contact, like why it is acting like a Schottky contact. But now the questions that we will be doing will be from diode, because we will be more interested towards the depletion region width, etc. So since we know that we this metal have a very high in number of electron as compared to this N, so I hope we have already covered that we will have a very smaller depletion width here or even negligible, and we will have a more depletion width here. This is what we have already covered in the previous classes also. I hope
Yes,
you,
sir. Yes.
yeah. For Schottky or for PN we have NAXP is equals to NDXN. Wherever is higher doping, we'll have a smaller width. So for metal, this ND plus is very, very higher than ND. So we have all the depletion region width for the N bar, for the in the N type or in the N side, sorry. So is your doubt clear?
Yes, sir.
Okay, fine. So this is the first question, which is very basic. So which is the metal work function, or sorry, which is the work function of a material? So quickly let me know the answer to this. I hope we are very clear about this already. Yeah, so C, so energy required to move an electron from Fermi to vacuum is, yeah. So this is the metal work function. Uh, so if I talk very quickly about the, again, the affinity, so it is from conduction band to vacuum, the energy required to move an electron. So that will be affinity, electron affinity, and the work function is Fermi level to vacuum. Yeah, so let's move ahead now. Okay, so we have a question now. Maybe you will try to solve it, obviously, but let me give a very brief overview. So we have a Schottky diode now, which is made from a metal N-type semiconductor. So we have a metal and we have N-type. And the doping of the semiconductor follows an abrupt profile. So this is a keyword here, abrupt profile. And the metal work function is greater than that of semiconductor. So we have a case phi m is greater than phi s. So we need to tell what will be the charge configuration look like. So we have all the four options. You can give it a thought and let me know the answer in the chat box. You can take 1 or 2 minutes to try it out. Otherwise, I'll solve it. Okay, so already have answer C. Do you want to give it a try or explain why have you chosen C? Anyone? You want to give it a try? Why it will be C?
On the metal side, there wouldn't be any charge developed, space charge region.
Yeah. So the first of all, at the metal side, that is very correct that there will be no space charge region. As I said, that the doping is very high. So this and this cannot be the answers. And now the why C, because we have a abrupt profile for the semiconductor. So I hope you are all aware that we have talked about this, that for a PN junction also, if we have a abrupt profile, the charge density looks like this. Abrupt means we have abrupt change, and we have for linearly graded it looks something like this. If it is linearly graded at both the sides, obviously. So for abrupt profile, we only have a single option, which is C. I hope this is clear, and this is, I guess, very easy. Um, yeah. So now the same question with some changes in it. You can read the question and let me know the answer maybe again in 2 minutes. This is very easy. You can give it a go and type your answers in the chat box. Yeah, I want maximum participation, so all of you try to get the answer. So I've got one as B. Others also you can try and type your answers in the chat box. Okay, so I've got two answers as B. So we have again given a Schottky diode for a metal N type. So let's say this is metal, this is N type. The doping of, okay, so now the doping of the semiconductor is following the linear graded profile. That is, it is already a function of X, linearly graded, something like this. And the metal work function is again greater, so it will be Schottky. So we'll have no space charge again for the metal side. So this is not correct, this is not correct. Again, so this is was the case when we had the abrupt profile. So the answer would be option B, because we have a linearly graded profile at the semiconductor and there's no space charge region at the metal side. So I hope this is clear to everyone. This is very easy to. Is it clear?
So what could be an explanation for the sudden rise in charge at origin?
Okay, it is not suddenly rising. So you can see. Okay, fine. So if I make, let's say I'll explain first of all for a p junction. So what we have for a p junction, sorry, in the depletion region, let's say Na and Nd, they both are, let's say, equal. So we have some acceptor ions left in the depletion region, and we have some donor ion left at the N side. So what we do is, for this particular N side, we have the charge density as Q and D, and for this side we have Q and A. This is what we have discussed. So this is what we say, that this is Q and D, this is ND, and this is what is Q and A. So there is a gradient in terms of the positive and negative charge for the PN junction also. So if I talk same for the metal now, so let's say this is metal and this is N type. So metal will not have any, sorry, metal will not have any space charge region because of its high doping, and we'll have some doping left for the ND. So this is why we are experiencing this. So let's say if I'm talking abrupt profile only, so we have this ND again here, which is QND. This is charge density plot versus position. So that is why there is this gradient change. So that is what we call as diffusion. So diffusion current, we know that this is change in the doping concentration with respect to the position. Does it make sense?
Yes, sir.
Okay, fine then. Maybe we can continue. Yeah, so this is a good question. So this will give you some more idea. So we have the equilibrium energy band diagram for an ideal metal semiconductor contact given. You need to answer the below questions. So the relationship between the metal and semiconductor work function and the type of contact formed for the figure A. So this is figure A. You need to see which is phi m greater than phi s, or it is if it is less than, and if it is ohmic or if it is Schottky. So Schottky is also known as rectifying contact because of the barrier. It is rectifying, and yeah. So maybe you can take 2-3 minutes and let me know what could be the answer and why it should be the answer. So I've got one is C. Let's wait for some more answers and then we'll see. So maybe I can give you a hint also. So we have a band bending move upwards. So what you can try it out is, let's say this is vacuum level. I guess we have already done it, but for your understanding, so let's say this is Q phi m. What you can try is you can take two cases, one in which the Fermi level is over. So let's say this is EC, this is EV. So that will be making this phi s, phi m greater than phi s, and you can make the band diagram, the contact diagram. And similarly, you can take another case in which this phi s will be coming below that, and you will see that which band diagram is looking like figure A. So this is the hint that sorry, I was on mute, I guess. Uh, so what I was saying is, to get to know to the answer, you can try two cases. One is in which phi m will be greater than phi s. You can try it out like this. This is what we have already done in the initial part of the class. So you will get to know that which band diagram is resembling to which case. So you can take more time and let me know the answer in the chat box. I guess I've got one answer as C, which is phi m greater than phi s and rectifying. I'll wait for 1 or 2 minutes more and then I'll solve the same. Anyone else with the answer? Fine. So this is what we have already done. So I got one more as C. So the electron will flow from higher Fermi level to lower. So that means this will go lower, so the band will move upwards. So there will be a barrier, I guess we have done in the initial part, if I made, yeah. So this was a diagram. So this was the case when we have phi m greater than phi s, and we reached to a conclusion that we had a barrier which is stopping the electrons from both metal and the n-type side to go from metal to n side. So that is why we have a Schottky contact for the case when phi m is greater than phi s. So I guess figure A looks exactly the same. Yeah, so what I can write is, so this will be the barrier height phi b. This will be VBI if you are all aware. Yeah. and this will be phi m. So it has been aligned, so this will be, sorry, phi s. So this is the same case, which is option C. Is it clear to everyone? Any doubts here? Please let me know if you are having any doubts.
No, sir.
Okay, so if not, please let me know the same for B, which will be the case. We have already discussed this also in the class, so give it a go and let me know what will be the case for the figure B. So we have ohmic and metal work function will be less than semiconductor work function. So yeah, this is the exact case in which we did took phi m less than phi s, and what we had is we had the band diagram which was band lower, I guess. Where is this? Yeah. So this is the case. So we don't have any barrier. Oh, sorry. And what we had, there was no barrier. There was no Schottky barrier in between these, and it was ohmic contact. And this was the case when phi m was less than phi s. So this was the next question. That is why I was waiting. So for figure B, what we have is option A is the correct answer. I hope this is very clear. So let's move ahead then to do some numerical problems also. So now we have the copper is deposited on a n-type silicon substrate. So metal with n-type silicon substrate, that is n-type semiconductor, to form an ideal Schottky diode. The work function of the copper is this. So phi m is given, and the electron affinity is also given. Something and something. You need to calculate the barrier height. So you can take 1 or 2 minutes and let me know the answer. Any idea about the answer? Okay, so maybe I'll explain a bit using the diagram above. So let's say this is the diagram. So this is what I have already told, that this is the barrier height. And what you can say is this is VBI, right? And this is nothing but EC minus EF, this particular difference. And if this is vacuum, so for this particular case, if this is the vacuum level, from conduction band to vacuum, we have what we have is work function. So what we can write is basically, sorry, what we can write is, maybe I'll make the vacuum over so that there will be no confusion. So let's say this is the vacuum level. So from vacuum to metal, we have phi m. This is the barrier height. This is VBI. This is EC minus EF. And from here to here, we have the electron affinity. Is there any doubt in the diagram that I have just labeled? Is there any doubt? Please let me know. Am I audible, guys?
Yes, sir. No problem, sir.
Okay, so if there is no problem, then what we can say is this phi b is nothing but the difference of phi m minus the electron affinity. Can we write that?
Yes, sir.
Yeah. So where is the question? Yeah. So what we have been given? We have been given phi m, that is 4.65, and we have been given electron affinity, that is 4.03. So barrier height will be nothing but 4.65 minus 4.03. That will be 0.62 electron volts, which is option B. So now we need to calculate VBI. So yeah, give it a try. Maybe I'll explain more. So we need to calculate this VBI, right? So VBI will be nothing but, sorry, give me a moment again. Yeah. So maybe I can use some different ink. So you can clearly see this blue line. So can I write VBI is nothing but, sorry again. So can I write VBI is nothing but this phi B minus this difference, that is phi B minus EC minus EF. Can I write this? Is there any confusion?
No, sir.
Okay, so and can I write EC minus EF as EG by 2 minus EF minus EI? I'll let you know how I've written it. So this difference is EG by 2, and this difference is EF minus EI. So what I've written is EC minus EF is EG by 2 minus EF minus EI. Does it make sense to everyone? Please, if you are confused, please let me know
Yes.
right now. Okay. So if it makes sense, then the question is asking about VBI, which is phi B minus, first of all, EC minus EF. So this phi B minus EG by 2 minus EF minus EI. And we know that EF minus EI is nothing but, since this is N type, so it will be VT ln ND over Ni. Sorry, this is P type, I guess, right? Is the question. Yeah, so this particular thing will be N type, so this will be VT ln ND by Ni. Yeah. And I guess we have been given everything in the question. The barrier height we calculated was 0.62 electron volts, and we have everything. So yeah, and EG, I hope you know that for silicon it is 1.1 electron volts, 1.12 exactly. So give it a try and let me know what is the answer that you are getting for VBI. Is it fine with everyone? I hope you are able to understand this. Please let me know and then I'll give you some time. Is it fine?
Yes, sir.
Okay,
Phone
fine.
here.
You can take 2-3 minutes and let me know the answer. I've got one answer as 0.42. So let's calculate. This was straightforward calculation. So we have 5e, which is 0.62. This is 0.56 and 0.026 ln nd was what? 10 to the 16, and then this is 10. So this is 10 raised per 6 only. This will be 0.62 minus 0.56 minus something. 6 times of 2 is 12. 12. Some value will come, and this will be less than 0.62 for sure. So this will be 0.429 electron volts, which is approximately 0.43 electron volts. That is option, whatever this is, last option. So this is how we have got to the built-in potential now. Is it fine with everyone? Kindly let me know, is it fine? Okay, so let's move ahead. So now again, for the same question, for the zero applied bias, we need to find the depletion width. So I hope you already know the formula to this also. Please let me know if you are trying, and then I can give you again 2-3 minutes and let me know the answer. Do you want to try? Please write in the chat box. Am I audible, guys? Hello. Do you want to try, or I should solve the same?
We will do
Can
one.
you start?
Okay,
Okay.
fine. So yeah, take 2-3 minutes and let me know the answer. Mhm. Can anyone tell what formula they are using? Uh, you can open your mic and let me know. Anyone?
Square root of 2 ES VBI by QNB.
Square root of, sorry, can you repeat?
Under root
Yeah,
2 epsilon s VBI by QND.
yeah, yeah, that will be the formula. So let me solve it if you've not got the answer till now. So this will be, sorry. 854. 2 epsilon s, whatever they have given, by Q and D times VBI. VBI was what? 0.43. So this will be in centimeter basically. So this will be 5. This will be 11. Yes, 10 square minus 5 will be there. 10, 10, be something 2.375. Will be 0.2375. Okay, 10 4 centimeter, and this is in nothing but micron. So this will be 0.2375 micrometer, which is option A. I hope it is fine. This was a direct calculation. You can again check later. So if you move ahead, then we have, I guess in this week's only we have some question of MOSCAP also, but I'll skip it for now because I'll be teaching it tomorrow. The main topic for the tomorrow's lecture is MOSCAP only, or MOSFET. So we can skip these two questions for tomorrow, and maybe let's come to some of the questions that have been given in this week. So we have a question. This is, how does the depletion region of a Schottky diode change under reverse bias? So can anyone tell what will be the answer? Yeah, so I've got already got C. So that will be correct, as we have seen for any junction that if we apply a reverse bias, let's say this is PN. So what happens is these holes will get attracted here, and we have a widened region for P side, and similarly a wider region for N side. So on applying negative or reverse bias, we have a widened depletion region. This is very straightforward. So yeah, option C will be correct. So now we have again a MOS capacitor, so that will do later, maybe tomorrow. Just skip it for now. Okay, so we have just solved a similar question, so you can give this a try. We have a contact between tungsten and n-type silicon. Nd is given, temperature is given, work function is given, affinity is given. You need to answer both the questions. So you can take maybe 3 to 4 minutes and let me know the answer to both the problems in the chat box. Okay, so I've got answer from one student. Maybe I'll wait for some more time for other students and then we'll solve it together. Okay, so question 6 is very straightforward. The barrier height will be nothing but work function minus the electron affinity, so which is 4.55 minus 4.01, which is 0.44 electron volts, which is option 0.54 electron volts, which is option A. 7 will take some time, so let me know the answer for that. Maybe one or two students, if they give, then difference between barrier height and barrier potential. Yeah, so they are the same. The We are defining it by height, but the it is nothing but the potential barrier. So that is why we call it as barrier height. But it is by default potential in terms of semiconductor physics. Barrier height and barrier potential are the same thing.
Sir, but we denote it with different letters, right? Phi B and VBI.
Oh no, VBI is built-in potential.
Okay. Oh.
Yeah.
Yeah, that's what I meant, sir. I'm unable to understand the difference between barrier height and built-in potential.
Oh, okay, fine, fine. So you can see it clearly here. Yeah. Here you see that we have a barrier at the metal and semiconductor. So this is barrier height or barrier potential, if you want to say it. And VBI is nothing but this. Once we have this band bending, so from vacuum or to from the top end to the conduction is VBI. Maybe I can make it very clear with PN junction to you. Let's say this is a Fermi. This is EI. Sorry. So this is EI. This is EI. So this is P side. This is N side. So what we have is we have this EI minus EF as phi P, if you remember, and this is phi N. And this particular difference, sorry, this particular difference from here to here, phi P plus phi N was VBI, if you remember the classes, and this is what exactly is this difference, VBI, from the top of the conduction band of the either side to the conduction band of either side. So this is what I have written, the conduction band, something like here to here is VBI, that is what I have written. And the barrier height is the complete barrier height that we are getting towards the metal side. So there is a difference of this EC minus EF here, if you can see. Does it make sense?
Yes, sir.
Okay, okay.
Sir, so
Yeah.
in the case of metal semiconductor Schottky junction,
Yes.
electron on the semiconductor side and an electron on the metal side, both will see different barriers, right?
Yes, yes, exactly. So for
Okay.
semiconductor, we'll see the barrier of VBI, and from the metal perspective, we'll see the barrier of phi B.
Okay.
Yeah. So what we were doing is we were doing, yeah, this. So again, from that diagram only, we'll get to know that VBI is nothing but the barrier height minus that particular EC minus EF. So we have done this similar question. So this is nothing but EG by 2 minus EF minus EI. And this is phi B is, sorry, minus EG by 2 minus VT ln ND over NI. So you can solve this. I guess you have already solved this. So anyone else who has got the answer, it will be 0.54 minus 0.56 minus 0.026 ln ND. What is ND? Again 10 is per 6. Okay. So is it 0.34 that you are all are getting? I'm not sure. I've not done the calculation. Please confirm. Is it 0.34?
Yes, sir.
Okay then. So option B will be the correct answer to this. Yeah. So this is the same. Okay. So now we have got one more thing, which is We have the IV characteristics of three different devices, 1, 2, and 3. So I hope you all know now what will be what. So let me know the answer quickly, and then we'll go ahead. E. So yeah, okay. So I'll wait for some more answers. So I've got one as E, which is the last option. Give it a try, maybe take 1-2 minutes. Okay, again last one. So yeah, don't let's just not waste much of time. So this is ohmic contact. We know that this is V equals to Ri, the linear relation, which is already only given in this option. So by that only you can say that option E is correct. But for Schottky, we'll have a reduced pinch voltage, that is VBI, because of the higher doping. And for PN junction, it will look like this. So basically, the Schottky diode shifts the IV for Schottky diode is a shifted left version of the PN diode. So option E will be correct.
Sir, will it be always a short key will be shifted left side
Yeah,
with respect to PM?
yes, because we have a higher doping concentration here. The gradient that we have is more here. So we'll achieve the forward bias very quicker as compared to a PN diode. So that is why even if you go towards the reverse bias also, so I guess so we'll have the case like this for Schottky and we'll have the case like this for PN. So the Schottky will have to be able to bear more reverse saturation current as compared to PN. So it is always left shifted for the Schottky, and the right one will be the PN if we plot it on the same plot, on the same axis.
Okay.
Yeah, so I guess we have covered the main part. So we have some more questions that is basically dependent upon the MOS cap. So I hope you are all aware that we'll be again having a session tomorrow. You might have got a notification. Is it there? Uh, did you get the notification for the session for tomorrow?
Yes, sir.
Okay, yeah. So I'll not be taking the class on next Tuesday, but instead of that, I'll be taking the class tomorrow. And in that class, what we'll be doing is we'll be covering the, I guess, the most important topic for VLSI or for this course also, which is nothing but a MOS capacitor. And that will be basically leading to a MOS transistor or a MOSFET. So what I ideally want is please try to don't skip this particular class that is for tomorrow, because if you won't be able to attend this class, then there are all the other lectures that are dependent upon this only. So once you will be able to get this working of the MOS capacitor, then you will be able to maybe clear any particular round that you will be covering or giving for your VLSI interviews, or if you want to pursue something in the VLSI or the microelectronics domain, maybe the research part also. So even after PhD that people do, what they generally ask is the basic question from MOS capacitor or MOS transistor only. So this is as important. So that is what I'm trying to say. So please don't try to skip. Please try to attend tomorrow's class because that is the most important one. And for this week, I guess we have covered most of the things that are important. The most important was a metal semiconductor junction only. So I guess we have already covered that aspect, and I hope you are able to get the Schottky also, how these barriers are getting made and why it is ohmic for when the work function is less than the semiconductor for metal and type semiconductor junction, and these profiles also. So maybe I can give you a very short gist. I guess now you will be able to get the flow of this course, like how we went from a single dope bar. Like if you remember, we initially started with the band diagrams for N or P type of bars different, like separately. Give me a moment. Yeah, which was this EF minus EC over KT. Then we had one more relation which was exponential of EF minus EI over KT. We used to do the problems that calculate the distance between the difference between the Fermi level from conduction band, which is this EC minus EF. This is EF minus EI. Same goes with P. We will have some effective conduction of effective density of states for this valence band, and the same will come here. It will be EB minus EF, and this will be EI minus EF. And then how we went from the single to the contacts. So what we did is we joined this P type and N type together, and we see that there is a difference in the band diagrams, how these are made, what is the barrier that we are getting, that we were terming as VBI. Then we even go from for isotype junctions like N plus N, which is, let's say this is 16, this is 15. And then ultimately we went from metal to N type. So metal is very high ND to N type, which is, let's say, 10 is for 16 in general order. So this is how the flow is going. So we went from single doped wire to the contact PN contact, then different type of isotype contact, then from metal to N type. So this is all what we have done is why? Because of this particular thing, which is MOS gap, in which what we'll be having is we'll be having a metal, we'll be having an oxide in between, and we'll be having a semiconductor. So this is nothing but a metal oxide semiconductor capacitor. So this cap means capacitor. So we'll be learning how it is acting like a capacitor in tomorrow's class, and we'll be seeing what are the basic characteristics that we have for it and why is it very important. So I again request to not miss tomorrow's class, that will again start from 5 p.m. So for now, if you have any doubts in this semiconductor junction topic, you can ask. Otherwise, we can dismiss today's class a bit earlier. Yeah, maybe you can think about it, and we'll dismiss the class in 1 or 2 minutes. If you have any doubt, you can ask.
So can we form junctions with metal and intrinsic semiconductor?
Yeah, junctions can be made by anything. So intrinsic by intrinsic. So let's say we have a diode basically in, I guess in the syllabus also we have this pin diode, which is nothing but a junction for P type, intrinsic and N type. So what it will do is, okay, so that will need some clarification. So you can go through the pin diode, in which what we are doing is we are making the junction between P and I and I and N together. So this is one of the like topic, I guess, for this week also, if I'm not wrong. And why do we use pin diode is, give me a moment. Yes, I have something for that. Yes, I don't have the notes for that right now, but yeah, the basic answer to that question will be yes, we can make the junctions for sure. We do have in fact, we have PIN, we have PNN plus IP. We can make any junctions. It's just all about the band diagram. If you are able to make the band diagrams, you can realize how the junction is getting made, how the barrier is coming in between the P and I junction. So, uh, in fact, that is a very good question. So, what I'll expect is maybe for tomorrow, all of you should come up with a band diagram for this P, I, and diode only. Like, sorry. So P means P type, N means N type, and I means intrinsic. And you can mail your all of you should mail me the band diagrams at my mail ID before the class. So this is my mail ID. You can type it down. Again, I guess I need to write it again. So this is my mail ID. So let me write clearly. So you should send me your screenshots for the PIN diode, like how is the band diagram coming, and you should be explaining that why it is like that. Maybe a single A4 sheet can do, and you should send me it before maybe 4 p.m. tomorrow. That will be great, and we can discuss that in the class. That will be maybe even more interactive. That will make the class even more interactive. Does it make sense to everyone? Is it fine?
Yes, sir.
Okay, that would be
So
great.
then, recently you drew a IV Cara of diode. Could you just take that diagram?
IV
IV
of
diagram. Yes, sir. This slide.
okay, okay, okay. This slide, yeah.
Here, overall, considering the forward bias and the reverse bias, it will be a continuous graph, right?
Yes,
Have you
yes.
taken different scales
No,
on
no,
either
the
side?
scales are same. It will be a continuous graph. So, do you see any discontinuity? That is what you meant?
Yeah, at the origin, it will be a
Okay, fine.
exponential graph, right?
Yeah, yeah. So let's say I'm making for p-n junction, so it is exponential, and we know that it goes like that in reverse bias, and once we reach this saturation voltage, it's get fixed, this particular reverse saturation current. So it is continuous only. Does it make sense?
Yes, sir. But the shape, uh, I was just confused about the shape
Where do you
of
see the
the graph.
discontinuity?
Um,
Venn diagram is available
at the
in the
origin,
textbook for PNI.
Sorry?
PIN. Venn diagram for PIN is available in textbook.
Is available in where?
Is textbook.
Yeah, yeah. So I guess it should be available in Neiman, and if not, it should be there in Benji's treatment. You will surely get it. And again, coming back to this discontinuity, maybe I'll make it more smoother. That will make more sense, I guess. So it is like this only. If you so we will have a very exponential rise, and then once this this saturation current, it like kind of soft breakdown. This is what I meant. And for the
okay,
PN junction, it is shifted towards the right, and it will go it will have a higher breakdown, and it will go down after this. This is what I meant. It is continuous. There is no discontinuity there.
okay.
Yeah,
Thank you, sir.
yeah. Well, so I guess we can dismiss today's session, and we'll meet again tomorrow at 5 p.m. All of you should mail me this PNIN band diagram. That will be great. Okay, so thank you everyone for joining. Let's meet again tomorrow. Yeah. So bye bye. Yeah. Thank you everyone.